Start? Yeah. Yes. Welcome to the distinguished webinar series in artificial intelligence and cybersecurity, which is established by UNDC2SR and SEECS. Welcome, dear Dr. Simone Silvestri. It's a great presentation that's titled as Residential Energy Management with Human in the Loop. Especially the human in the loop factor is very critical, as you know, in terms of today's AI-based systems. So I'd like to, first of all, introduce dear Dr. Silvestri. Dr. Simone Silvestri is currently an associate professor in the Department of Computer Science of the University of Kentucky. Dr. Silvestri's research interests are cyber physical human systems, Internet of Things, terrestrial and aerial mobile networks, and network management. His research is funded by several national and international agencies such as NIFA, NATO, and the NSF, and he received the NSF CAREER Award in 2020. He published more than 90 papers in international journals and conferences, including IEEE Transactions of Mobile Computing, IEEE Transactions of Smart Grids, ACM Transactions on Sensor Networks, IEEE INFOCOM, and IEEE ICDCS. He served in the organizing committee of several international conferences, including as general co-chair of IEEE ICNP, technical program co-chair of IEEE SECON and IEEE SmartComp, as well as IEEE DCOSS. Yeah, thank you very much for accepting our invitation, dear Dr. Silvestri. We are able to see your presentation now, so it's up to you. You can start whenever you are ready.
Okay, thank you very much for inviting me, and thank you very much for the kind introduction. I made too many slides for today, so let's start right away without wasting time. So as you may imagine from the... Why this is not working? 1 second. Okay, there you go. As you can imagine from the title, the main topic of this talk is dealing with energy management for residential buildings. And the energy consumption of residential building has been constantly increasing, and you can see it in this graph, for example, and it is responsible for more than 20% of the total energy consumption in the United States. It is expected to further increase in the next years, and this is especially true for developing countries in which, of course, the development of buildings is even more pronounced than here. So these days, power systems are significantly changing. We have introduced smart grids, advanced metering infrastructures. Also, appliances are becoming increasingly interconnected. We have smart thermostats, smart outlets. Some houses are equipped with generation of electricity through, for example, photovoltaic and solar panels. Some houses also are equipped with batteries, so they can store electricity as well. And also, we have the introduction of virtual power plants. So there has been a lot of research done using these new technologies. However, most of this research has not considered the complexity of human behavior that affects the energy consumption in the residential sector. So they've mostly targeted engineering metrics, but they have not considered the complexity of human behavior. And there are recent social science studies that show that there is a significant failure in acceptance of these new technologies, and the behavior could be negative towards this new technology and even cause an increase in energy consumption and even an abandonment of these systems overall. So our objective in this research is to overcome this limitation by explicitly including the human in the loop in residential energy management by taking into account the user behavior, perception, and psychological processes. So addressing system and house level energy needs, while at the same time considering the complexity of human behaviors and perceptions. And in this talk, what I'm going to do is to give you 3 examples of papers that we have recently published in which we address this type of research, taking into account the human behavior in residential energy systems. So the first one is a paper that we published in Transaction Evolutionary Computing recently. And so here the focus is peer-to-peer energy trading. So as I was mentioning before, houses are equipped with generation of electricity through, for example, solar panels. So generally, this electricity is either used at the house or is sold back to the grid. This is what happens most of the time today. However, we envision the power system will be able to allow soon, and there are even some startups that are investigating this, the exchanged of energy among users. So you can produce some energy in your house, and then you can sell it to, for example, your neighbor that doesn't have solar panels. And so there are several advantages in this, because you can reduce, of course, your energy bills by selling some of the energy that you produce. You reduce the cost for the actual power system, because you do not need to invest so much in infrastructure. And also there is a save of energy, because the energy is produced and consumed locally versus producing in a large power plant and then transfer it all the way to your house, which includes significant losses. So of course there has been some research in this domain, but most of this research requires active user involvement, which is generally not really an assumption that is possible to do. Also, they assume that users are rational agents, so they always take the best decision. But in practice, usually, generally, users deviate from this perfect rational behavior for several reasons, such as lack of information, lack of time, lack of interest, etc. So what we want to do in this work is to actually incorporate the user perception in peer-to-peer energy trading. So how do we do that? We rely on some models that we inherit from behavioral economics and specifically from prospect theory. So prospect theory is basically a branch of behavioral economics that tells you how humans perceive losses and gain. And I think the easiest way of understanding this is by looking at this graph here on the right, in which you have a reference point. And then if you have a loss with respect to that reference point, you perceive that loss much more greatly than the corresponding gain that you may have from the same reference point. So humans are not rational, and the way in which they perceive losing or gaining $5 is not the same. And basically what prospect theory tells us is that losses are perceived much more strongly than gains. So how to include this into the peer-to-peer energy trading? We design a system in which there are prosumers, so users that can produce and consume energy. Then the sellers, so those that produce energy, decide a certain price, and the system allocate the demand and production based on an optimization problem that I'm going to present in a moment. And then there is a subsequent component that decides what is the best selling price for sellers depending on their previous experience in the market. And I'm going through each of these components in the next slide. So first, let's consider sellers. So here, as we said, we want to maximize their perceived utility. So, and this is expressed as the deviation from their reference price, which is the price at which they would like to sell energy. So we formulate this optimization problem in which the objective is to maximize the prospect theory value function, which is basically the utility function of the users defined according to prospect theory, as I said before. You can see the big formulation here on the left, but I mean, don't worry too much about it. It's basically a nonlinear function that models gains and losses in a non-symmetric way. So we want to maximize the utility function of the users while matching supply and demand, taking into account losses and various system constraints. So I'm not going to the details of each of these equations, but basically that's what you're doing, matching supply and demand by maximizing the value function of the sellers. So this problem is nonlinear, and we also prove in the paper that it's NP-hard from a reduction from the general assignment problem. So of course you cannot solve it optimally, especially for big networks. So we rely on a differential evolution algorithm to do that. And so what this algorithm does, again, it tries to match supply and demand of energy by maximizing the perceived value function. And I don't know how familiar the audience is with evolutionary algorithms, but basically what you do is that you create a bunch of initial solutions, and then through two operations of mutation and crossover, you generate new solutions. Then you check if they meet the constraints of your problem, and if not, you can either discard them or fix them, and then you compare the fitness, so basically the value of the objective function that you want to maximize, and you keep track of the best solution that you have found so far. And you keep doing this for a bunch of times until you decide to stop. So this is the algorithm that we use to match supply and demand and maximize the value function. Of course, this algorithm is polynomial since it's basically a bunch of loops that are nested with each other. Then we also need to take into account the sellers. So here, the sellers may not be equally competitive. So users may decide to sell their energy at a certain price, but they do not really know what is the best price to sell. So what would be a competitive price for the market? And it's not just about the market, because electricity is not something that you can buy and sell like an Amazon package, because it has a cost of transfer electricity from where it is produced to the where it is actually used. And so this includes some system constraints that we need to take into account, that can make some sellers, some producers of electricity less competitive with respect to others. So here we have a reinforcement learning approach that basically tries to find, with respect to the target price of the user, a price that is actually competitive and allows to sell more energy. We also proposed, this previous algorithm is based on Q-learning. And as you know, Q-learning sometimes has problems when the Q table tends to be too big. And so we also proposed deep Q network in order to address this issue, in which basically we have two networks, a learning network and a target network. So the way in which this works is that the learning network says what the new price of selling energy should be. Then this is translated to a reward, which is basically depending on how much energy you're actually able to sell at that price. This goes in a replay buffer, and then the replay buffer is used to train the target network. And then the target network is used to train the learning network by using the prospect theory value function again for the sellers. And the reason why we have two networks is that we want to avoid the target moving problem, in which basically you are trying to learn something that keeps changing, and this may prevent the overall learning to converge. Let me show you some results briefly. So here we compare with a couple of other solutions. One is called Rule, which is basically a greedy energy allocation, and the other one is called Zoo from the others, which tries to minimize the transactions loss. So in the first graphs that you can see at the top, we are changing time. So these are basically results over time. And the results keep going up and down because the energy production over the years could be higher or lower depending on the specific season. And our line that we are proposing is actually the blue line up here. This is the regular Q-learning, and the yellow learning is the deep reinforcement, the deep Q-learning. And so basically what our solution is able to do is to find a good compromise between the maximizing the value function of the buyers, while at the same time getting a good compromise in terms of the revenue that the sellers can achieve. And so we achieve this good compromise with respect to other approaches that maybe can get higher benefits from the sellers, but then significantly penalize the buyers, or vice versa. And so in the bottom results, also we studied some scalability of our approach with respect to the number of buyers and sellers, and the same applies also as the network grows. So this concludes the first application of this overall philosophy of trying to take into account the user when and user perception when dealing with energy management systems. Now let's move to the second topic. So here, this is another paper that we published on transaction cyber physical systems in the last couple of years, and the problem deals with user-centered learning for appliance recognition. So in many cases, especially when we deal with a residential environment, we are learning from humans. For example, this is true for activity recognition, voice recognition, appliance recognition, etc. So most of the time we deal with machine learning. What we do is that we train these machine learning models offline. And this means that we have a bunch of training data, we use it to train our model, and then after that, we use it with the new data or other data we have available in order to calculate, for example, accuracy, etc. So is this always possible? So this may not be always possible. For example, if whatever you're trying to learn does not generalize very well, so your training data does not very well represent the testing data, or if you just do not have any training data to begin with, like, well, what are you going to do? Or, for example, if the inference domain can be very dynamic, so new things come all the time, and so you need to keep learning, and you cannot just train once and then be done. So researchers have proposed something that is called stream-based active learning, which is a kind of a different type of learning approach in which data is not available at the beginning, but data arrive in streams. Then these unlabeled samples go into the learner, and a learner can decide, should I ask an expert, that usually is a human expert, to label this data or not? So for example, this finds application in the medical field. Let's say you take an X-ray of your leg, and you want to decide, and the learner needs to decide if that leg is broken or not. Then for some samples, it can do this easily. For some others, it can't. And so you need to ask a doctor and say, yeah, this leg is broken or this leg is not broken. Of course, it's a simplistic example, but it gives you the idea of a potential application of this. Of course, generally you have a budget, so you don't want to ask the expert everything, but only the most informative samples that will help you increase the accuracy and the inference accuracy of your model. So all the previous research in this domain generally assumed that the expert is someone that is always available and knows what he's doing. But what when we apply this type of machine learning into a residential environment in which we are learning from regular users that are not as involved as, for example, an expert or a doctor could be? So what can happen? So we may get noisy labels. So some labels may be wrong. The user may just decide not to provide a label when you ask the user to provide a label because maybe it's busy doing something else. Or for example, maybe more or less available in certain time of the day and less available in other time of the day. And also there could be differences among users depending on their schedule, depending on how involved they are with this type of systems, etc. So what we want to do here is to design new machine learning approaches that can learn and adapt to the user behavior and engagement during the learning process, while at the same time maximize the information gain and basically the accuracy of the inference capabilities of the model that you are designing. The specific problem that we consider here is the problem of appliance recognition. So as you may imagine, futuristic home, and actually you can even buy these on Amazon, are going to be equipped with smart outlets. So these outlets can collect the electric signature of the appliances. And our objective is to recognize what is the appliance that is being plugged in. And this could be useful for a variety of energy management technologies, such as, for example, demand response, energy saving, etc. So why this is not a good candidate for the standard type of offline machine learning in which you do the training and then you just do the testing? So here we have some preliminary data that we have collected. These are data over time of the current that is consumed by two appliances that you would expect to be similar, such as, for example, a Dell monitor and an LG monitor, or a Dell laptop charger and another Dell laptop charger. So they can be significantly different, even if from a more abstract standpoint, they're basically the same type of appliances. So we cannot just really train and test. Additionally, new appliances come up in the market every day, so it's very hard to have a training set that is sufficiently representative of the entire set of appliances that are available in a certain time. So how our approach would work is that the user plugs in the appliance, this generates some electric signatures, and then the learner needs to decide, should I query the user to get the label, or shouldn't I, and just classify this appliance to the best of my abilities? Also, we are going to have a budget that basically you don't want to ask the user too much and too often, because of course the user may not be available, also may feel overwhelmed by this continuous request. And also what we consider here is that the user may decide not to respond to a certain query because it's busy, it's doing something else, it doesn't care, etc. So to give you an idea of how users actually behave, there's a question and answer. I don't know if am I supposed to consider this now or at the end?
You can answer at the end.
At the end, okay. Probably. Thank you.
Yeah, you're welcome.
Okay, so just to give an idea of how users actually behave, here, this is this MPU dataset that is available online that considers more than 300 users, and they sent 10 to 15 times a day a notification on their phone, and then they ask the users to respond to this notification. Well, over time, first off, only 30% of these notifications were responded, and as you can tell, also the availability of the user is highly heterogeneous over time, and also is highly heterogeneous across users. So the way in which we model here a user is basically each user has a certain probability of responding at a certain time of the day, and this probability distribution could be different with respect across different users. And of course, it's unknown, so we also need to learn this. So our problem is to find what is called a query strategy that maximizes the accuracy of recognized appliances while by querying the most informative signatures, learn the user distribution of willingness to respond to our query, and at the same time, do not query the user too often. So how do we do this? We design an approach which is based on K active neighbors, and each point in, for example, the examples that you can see here, is basically signatures that come from an appliances. For each of these, we consider the informativeness and representativeness. That basically are two metrics that tell you, one is how well you represent an unknown part of the inference space, and the other one is how similar you are with respect to your neighbors. So basically how many neighbors you have. And to calculate the distance among two electric signatures, here we use dynamic time warping. That basically is a way of calculating the similarities between two time series that could potentially have different length. And also we try to predict the user engagement. Additionally, we introduce also a confidence score. So we want to try to understand, if I get a new electric signature, how confident I am of the label that my model would assign to this specific signature. If I am very confident, then maybe I shouldn't ask the user to label it, even if I have budget available. While if I'm not confident, then maybe it would be a good idea to do it. So with all this information, we design our adaptive querying strategy. So first we calculate a quality of the signature that we just received. And this combines informativeness, representativeness, and the confidence score. But then we need to do something else. And this is probably one of the interesting aspects of this problem. So as the system learns, the signatures that arrive change their quality. So something that could have a high quality at the beginning, just because at the beginning you don't know much of anything, may not be of the same quality later on as the system has learned more. So for example, let's assume that you use a lot charging your phone. Well, after a while you do that operation, the system has learned that type of signature. So that signature is not as the same quality at the beginning as it is at the end. Therefore, we want an adaptive query strategy that, given the quality of a certain signature, tries to predict what is the expected number of signatures that I will get that day that will have a higher quality. And this is what we try to do here. I mean, I'm not going to go into mathematical details, but basically we try to see how many signatures of higher quality I'm going to get. And then if I'm going to get less than my available budget, then it means that I can query the current signature. If I'm going to get more of those, then maybe it's not worth to get the current signature. And so basically the type of signature that are queried at the beginning are different of the type of signature that are queried at the end, depending on how the user behaves and which appliances are actually used. So in order to test this approach, we developed an Arduino-based smart outlet. You can see it in this picture here that can sample the current at different frequencies. And we have developed our own data set in which we have considered several appliances such as hairdryer, network switch, laptop, monitor, another charger, a fan, etc., at different frequencies. And also we have used another existing data set, which is called the Ego data set. We compare with two approaches. One is based on SVM, this is called OBAL, and another is based on convolutional neural networks. And so now let me show you some results. First, we study the user distribution. So how good are we able to learn how available is a user at a certain time? And we can do this, as you can see in these relatively simple results here, relatively well. So on the y-axis here, you have the probability that a user will respond at that time, and on the x-axis, the hours of the day. So these are two different users, and also heterogeneous users we can learn relatively well. Then we study some results over time. So here you have on the x-axis the days. So as the system keeps learning, because remember, these systems learn over time. So time is kind of an important component to study. And on the y-axis, we have the accuracy in identifying the appliances. Our approach here is CAN, is the blue one. And also we consider different budget settings. So how many appliances you can actually query in each day. So 3, 5, and 7. And as you can tell, our approach outperforms all the other ones over time. It is worth mentioning that the OBAL one is better at the beginning because it requires a lot amount for training. And the CNN is performs very poorly just because it doesn't have enough data to learn. So it would require much more data, as you can tell here, in order to start finally gaining some higher accuracy. But this training is just not available in a house by grading a few times a day. Okay, so this concludes the second part of this talk that I wanted to talk about. So now let's move to the third part. And so this addresses another issue, which is power conservation using HVAC, so heating and air conditioning, through reverse auction and machine learning. And this is a paper that we published at PERCOM and then published on extensions on transaction cyber physical system as well. So you may have heard of the recent outages that have happened in Texas and California in the recent years. So in Texas, we had a winter storm that caused a peak demand of more than 69,000 megawatts. And this caused the system operator to introduce what are called rotating outages. So basically they shut off on purpose some part of the system just to try to keep the demand more or less under control with respect to what they are able to generate. And more than 11 million people experienced some outages, and even some people died due to the extreme temperature that caused these demand peaks. And however, the outages just would shut down completely the electricity in a certain area. And so people were exposed to this extreme temperature, which is, of course, highly undesirable. It's something very similar happened in California, but instead of winter was a heat wave that hit California in 2020. Plus, these type of outages are increasing over time due to the change in weather as well. So it is well known that air conditioning is one of the components of your house that consumes the largest amount of electricity. And you can see it here, the first two lines are basically air conditioning and space heating. And this is especially true when we have an extreme weather event, because if it is extremely hot or extremely cold, your heating and air conditioning are working extra hours in order to try to keep the house at your desired temperature. So in order to reduce the demand on the user side, what you can try to do is to introduce some power conservation. So try to reduce the demand by having, for example, dynamic pricing. But this is sometimes ineffective, like it was ineffective in Texas, because people just didn't care about how much they were paying. They just didn't want to freeze. So actually what the ERCOT, which is the system operator there in Texas during that time, what they tried to do is to actually publicize on newspaper and social media a message telling the people to reduce their HVAC setting or heating setting in that case, in order to try to reduce the energy consumption. So of course, this is a very archaic and ineffective way of doing things. So what we propose here is a framework for HVAC power conservation, which is based on reverse auction theory. So there are two main actors, the utility company and the users. And when the utility company expects a peak in demand, it asks user for bids. So basically, we are asking the users, how much do you want to reduce your temperature of 1 degree? Let's assume it's summer, so it's hot and you want to reduce the setting of the air conditioner. How much do you want for 2 degrees, for 3 degrees, etc.? Users say, okay, maybe for 1 degree, I want $1, for 2 degrees, I want $3, and so on. Then these bids need to be translated at the house into an actual reduction in energy consumption. And this is highly house dependent. So depending on what are the characteristics of your house, reducing, for example, the size, I mean, it's probably the easiest thing to think, but there are many other characteristics as well. Depending on that, reducing the temperature of 1 degree can result in a certain energy consumption or energy saving or another, depending on many characteristics of the house. So we have an algorithm that does this. So basically translates a reduction in or an increase in the temperature with an actual reduction of energy consumption. And so this is sent back to the utility company that decides who the winners are of the auction, and then communicates this to the user that actually reduce their energy consumption. And I mean, the users here are not really involved explicitly mean, they might, but what we envision is that we have an energy management system in the house that takes into account of potentially providing the bidding according to a predefined profile, and also at the same time adjusting the temperature if the user wins the auction. So in order to select who the winners are, we formalize an optimization problem in which basically we try to reduce the cost for the utility company by selecting the best bids. So a trade-off, if you want, between the bids that provide the most energy saving and they're not too expensive, in order to make sure that the target reduction, that here we call PS, is actually met. Then given the set of winners, we have a payment rule that basically tells you how much you need to pay each user compared to, with respect to what their bid was. And so the reason why there is this payment rule is that we want this type of auction to have a certain property, and this property is called truthfulness. Basically, the idea is that each user has a certain amount that they would like to be paid to reduce their HVAC setting, let's say a certain amount. However, what is blocking a user to bidding a higher amount for that, with the idea that you would make more money, right? If maybe I would do it for 3, but I'm going to ask 5, because that way, I'm going to make more money for the same reduction. Alternatively, I may think, hey, I would like 3, but maybe I can ask 2 so that it's more likely that I'm going to win. So you can do that, but if the auction is truthful, this deviation from your reference price or target value actually incur a reduced utility, meaning that you may either make less money if you win, or there is a less chance that you're going to win because you're asking too much. And so this is something, of course, needs to be proven and depend on how the auction is set up and designed, etc. But we were able to prove it for this optimization problem. Also, we proved that it's individually rational. So basically, everybody has a non-negative utility. But unfortunately, this problem that I just showed you is NP hard. And you can do a reduction from the minimum knapsack. So we designed an heuristic in order to solve this same problem, so selecting the winners. So the heuristic is not particularly complicated. Basically, it's a greedy heuristic in which you rank the user according to a certain way that takes into account the cost and at the same time the corresponding energy consumption. Then it ranks the bids and then select the best bids according to that rank. And then we also design a payment rule. So here the algorithm is not very complicated, but if any of you at some point will try to design such auction mechanisms, you will see that it gets harder and harder to prove any property on your algorithm if the algorithm is too complicated. So here you kind of need to achieve a balance between how complex is your algorithm and what properties you are able to prove. So in this case, with this greedy algorithm, we actually were able to prove that this is a polynomial algorithm. It may not find the optimal solution, but it is actually truthful as well. So users do not have any incentive from deviating to the best, to bidding their actual value. It also is individually rational, and it is polynomial according to a certain complexity. So once the user has submitted the bid, as I was saying before, this bid is just a monetary value with associated temperature change, but we don't know what that means in terms of actual energy saving. And as I was saying, this depends on a lot of factors. Some depend on the house. So what is the house size? What are the materials that are used for that house? For example, the insulation. What is the window U factor? And these are also parameters that the user doesn't know. So there's no way of saying, okay, let's just ask the user and then we know this. At the same time, there are also external parameters, such as, for example, the solar irradiance, the wind, the humidity, that also affect that. So there are generally 2 approaches in the literature to deal with this. One is the white box, in which you have a bunch of equations in which you need to put all these parameters and then get the energy saving, but this is kind of impractical. So we follow here the black box approach, in which basically you have a machine learning model that you train over time with your house, and then you use it once a new data point is available. And so we call this the PSP algorithm. It's nothing too fancy. Basically, we use some relatively easy available features, such as, for example, the weather information, the house information in terms of thermostat set point, the new set point, and the inside temperature, and what is the hour of the day. And here we just use a simple random forest that perform really well. Also considering the fact that here you're getting data from an individual house, and so you don't really have a lot of data to train a big, for example, deep neural network model as well. Also, we have done some online surveys to see how users would first be interested in engaging with this type of energy management system, but at the same time, how users would bid. And we have used 200 subjects on Amazon Mechanical Turk. So it's actually interesting to look at the results of the survey. We have 79% of subjects that are willing to engage in this system, which is promising. But the bidding behavior is not linear and it's not uniform. So here on the x-axis, you can see how many degrees the users are willing to change their thermostat set point. And on the on the y-axis, you have how many users are willing to do that. And as you can imagine, fewer and fewer users are actually willing to have a big change in their thermostat setting. And you can tell that the relationship is not linear. At the same time, how much would they like to be paid to achieve a certain degree change? And also this is not linear. Of course, it increases, like if to a bigger degree change, you want a higher payment. But also you can tell that there is a lot of variability. So users really have different opinions about what is best and how much they would like to participate in this system. So in order to validate this approach, we use Energy Plus, which is the one type of energy simulator. It's very well known and very extremely reliable. We created several houses with different energy profiles in terms of energy consumptions. In total, we have 80 different houses. And we consider a period between July and September within a certain time. And then we allowed at most 8 thermostat change options, because as you can tell, users will not go beyond 8 anyway. So let me show you some results. First, we see how well we are able to predict the temperature change. So if I change 2 degrees in my house, how much energy I'm actually going to save. And so this is done by the PSP algorithm. And you can tell here that this is the percentage of error on the x-axis, and this is how many samples we are able to have within that error. And so most of the samples are within 10 to 15% error, which is much, much better than another approach that was existing in the literature that I think is cited down here. And this is true in terms of this distribution of error, but also in terms of explained variance, which is a metric that is commonly used when you deal with numeric predictions. Then we consider how well we do for the power conservation. So here we consider peak load period of 1 hour during a hot summer day. And we compare with an approach which was at that time recently published in INFOCOM. This was designed for data centers, but it could be easily adapted to our approach. So although this is an auction-based approach, that's why we picked it. So here we consider different penetration of this technology. So some users may just decide to not bid. And this is a very realistic scenario. So you should never consider, oh, everybody's participating in what I'm doing, because people may just not care. So, and here we consider first the objective value. So basically how much is the objective value of our problem. That, remember, we want to minimize the cost for the system operator, and then how much the system operator is actually going to pay to guarantee that the auction is truthful. So obviously, more people participate, better bids you can take, and the less you're going to pay. But you can tell that our approach, which is the green one here in both graphs, achieves a much lower payment for the system operator with respect to other existing approaches. Oh, no, sorry, wrong. So the opt is the optimum. GRAN is our approach, so the greedy heuristic. So optimum is what we would be able to achieve by solving the NP-hard problem, and GRAN is what our heuristics achieve, and the gray line instead is the comparison approach that we found in the literature. So still, we do much better, but there's still a significant gap that could be improved with a better heuristic. Then we consider a different setting of how much energy we need to reduce. So this is the percent of reduction that the system operator want to achieve compared to the expected demand peak. So of course, the higher is the percent of reduction, the more you need to pay users, because more users need to participate in the auction in order to achieve, sorry, need to win the auction in order to achieve that specified percent of reduction. So here you have again the objective value and the payment, and you can tell that both of them increase. And again, the green line is the optimum for both of them. The red line is our heuristic, and the gray line is the comparison approach. So in both cases, we do much better, and we are able to save a significant amount of money to the system operator. I think this is the last slide. I hope I am on time for this, for the expected time that I have a lot. And so now I'm open to questions.
Thank you very much, Dr. Silvestri, for your great presentation. First of all, we have some questions. I'd like to ask a question at this point before passing to the other questions.
Sure.
What do you think about the future steps here? For example, we know that there's a great interest in digital twins, and also existence the human factor in the simulation systems, and transforming them into somehow a digital twin-based applications are somehow remarkable, that application-based nowadays. So what do you think about the possible combination of the smart systems you mentioned and combining them into the digital twin framework, and still keeping the human in the loop as a main factor to track and manage all of these systems in terms of an application view? What are your perspectives about this?
I think it will be definitely advantage of integrating, for example, simulation with hardware in the loop, and trying to achieve this this digital twin. And the main challenge, which honestly is a challenge also in this type of research that we try to do, is that when you integrate users, like if you want to do it reliably, you should do that in their real life. So it's kind of hard to connect these two worlds, So what we are doing, and it could be digital twin, or it could be, whatever type of machine learning optimization that you're doing, and then integrating into the actual life of people. We had a paper that we published, I didn't present it today, in which we actually deployed our smart outlets in a home, and we tried to get the feedback of the users of what our algorithm was actually suggesting based on their actual utilization of the system. And first of all, it was a ginormous difficult to just set it up, going through the IRB, deploying the appliances, and then try to find a way of actually measuring their feedback that was scientifically meaningful, but also at the same time reasonable to us, to a user that is partially engaged with the system. So I think that it is definitely challenging in order to achieve something that is reliable when you are dealing with humans. That if you bring someone in a lab, it's never going to be the same that testing something in their own life. So, of course, we try to use realistic data sets. We try to engage humans as much as possible. We try to do surveys. But I think there is still more there to be done to try to deploy these techniques in the real world. Digital twin could be a possibility, but I still see significant challenges there.
Yeah, as long as the human factor is somehow a chaotic thing that which may be connected to the dynamic systems definitions, and still we have more spaces to cover everything you say. So it's another challenging thing, maybe for further research. So thank you very much.
Thank you.
Yeah, I will take a look at the other questions. Hamza Karim asks that about if energy transactions between prosumers is also including connection to grid, why the pricing is not regulated and fixed by some entity or body?
Okay, so the main reason there is really the market. So if you fix the price, and this is fixed by the grid, which is honestly what is available these days, it is much less incentivizing for users to participate, because so of course the grid sets the price depending on their benefit, but there is not really an open market that can allow producers and consumers to better benefit to what is possible. So of course, you can always buy the energy from the grid. So whatever you are selling needs to be less than what you can buy from the grid. Otherwise, I just buy it from the grid. But the price at which grids buy energy from users today, compared to the price at which they sell energy to you, there is a giant gap. So there is a significant advantage the user can get by selling energy to other users rather than selling it back to the grid. And actually, I mean, sometimes, for example, in Italy, where I'm from, the state provides incentive, so money to the energy companies to pay users more to produce energy. Otherwise, the amount that the system operator would pay is almost insignificant to make no difference in your energy bill. So either you use your energy or goodbye.
Yeah, you're right. Thank you very much, Dr. Silvestri. So I see also there's a great interest for your presentation, by the way. Ebenezer Roberts asked about the presentation, about your presentation, if it will be possible to be shared with participants. It's all
I
up.
can send it to you, no problem.
Yeah, we can share, or you can send it to me or to my mail, maybe, or they can be reaching to you out. I'd like to also say that.
Yeah, if somebody can send me an email and then I can just respond with the slide.
Okay. You can send it to me. My name .kose@und.edu. And also you can send to Dr. Prakash, of course. So we'll be all having in our lab. Thank you very much about that. So another question also, even including your request for the PPT to be shared, of course, by a researcher at Stony Brook University, working on human in the loop for optimizing microgrid operation. So I'd like to have one question at this point, like the microgrid operation may require more that human in the loop factor, of course, at this point. So how we can combine the XAI, explainable AI, at this point to ensure that the human in the loop is running properly in optimizing microgrid operations. This is just the question appeared in my mind. So sorry about that. But I'd like to ask you.
I'm actually submitting a proposal next week about this.
Oh, great.
I mean, I think there's a great opportunity to use explainable AI, large language models to interface all these optimizations that we have been doing for years in energy management system at the residential level. And so I think it's a relatively new area. There is not much work that has been done. There are some works that have been doing recommendation systems, but those are more it's just about providing users recommendation, but large language models today and explainable AI can say much more than just say, hey, do this. It's going to be I think much more powerful, and that's what we would like to achieve. Right? Really, we are submitting this proposal now, so I'm hopeful that could definitely open new dimensions, new goals, better integration between the system and the users by providing explainability. Because one of the challenges in using any of this system is trying to explain the user why.
For sure.
Money is a potential good way, but every single change in your behavior is going to be a minuscule change in actual energy saving that can change the grand scheme of things, or can help in a blackout, or can help reduce your energy bill over a year, but the single action is almost irrelevant. So it's hard to explain to the user why you should do this. So we can hopefully use this system in order to improve that.
That's a great potential, and it seems that the XAI factor with the human factor combined to be that just making the systems, even deep learning based systems, are all almost black box somehow. So it's having a great potential. Thank you very much, dear doctor. So there's one more question by Nirup. Thanks for your presentation, Dr. Silvestri. He says, in the context of application recognition, can you elaborate on how KAN can be made more robust to misclassification errors from users?
So this has to do with noise labels. So we did some testing to see how robust we were with respect to wrong labeling. But we did not really explicitly design in the algorithm something that takes into account and isolates those. I mean, honestly, it's possible, especially in a simple machine learning model, such as, for example, a k-nearest neighbor. After a while, so I'm trying to find the slide. There you go. After a while, these wrong labels will be outliers that you may be able to identify. Of course, under the assumption that the user is providing the wrong labels randomly without a specific purpose to mess up the system, because of course, if you have an attacker that tries to purposely make your classification wrong, then you may have more wrong signature than right signature, and then the system is going to say, oh, wait, okay, what can I do? I mean, this reminds me a lot, kind of the Byzantine type of situation in which you want to reach an agreement, and as long as you don't have too many, then you could be fine. And if you start having too many, then at some point you cannot reach an agreement anymore. And this is kind of similar type of problem. So here, this was sufficiently robust. I don't remember exactly the number, but maybe we tested up to 20%. 15% wrong labels, and it was fine. But I think if you start going higher and you don't include a specific approach to deal with that, then of course the problem could be higher and the accuracy would drop.
Yeah, thank you very much for your answers, Dr. Silvestri. So any other questions by the audience? I just would like to ask last time. I think there is no more any questions. So you may send your presentation to me, Dr. Silvestri. I can share as a reminder my name and my surname.
Yeah.
There's a dot between
down.
them. So thank you very much for your presentation and for sharing your valuable that PPT file and the content with our audience. So your presentation will be shared over our YouTube channel, C2SR channel, and you will be receiving a plug soon as a kind respect from our the lab and also the UND SEECS. So grazie mille.
There you go. Grazie, prego. Thank you very much. Thank you. You have my address for the. You have my address and everything for the plug. If not, just ask me.
Oh, yeah, sure. We'll be sending you an email if you need some more detailed information.
Okay.
I'll be in
Thank you so much. Thank you very much for having me.
Thank you very much. I'll be in Italy next month, so I will send your wishes to Italy also.
Okay, yeah, of course. Enjoy the trip.
Yeah. Thank you very much. Thank you. Have a good day.
Bye. Thank you.
Bye. Thank you.